So, do we remember from yesterday when I was on Desmos what the rational graph looked like? When we had 1 over x. Well, that marker's dying. It looks something like this, right? Do you remember that? I said get that stuck in your head, Josh and Chris, because that's what our rational graphs are going to end up looking like. So, in a rational function, what do you think needs to be true? Where does a variable need to be? In the denominator. You can have a variable in the numerator, but you need to have a variable in the denominator for it to be a rational function. So, for a rational expression, what we're going to be looking at is the quotient of two polynomials. So you're going to have a polynomial in the numerator. You're going to have a polynomial in the denominator. Polynomial in your numerator could be a constant monomial, which that would be the case over there, 1 over x. It could be a binomial with degree of 2, so a quadratic binomial. But you need to have a polynomial somewhere in the denominator for it to be a rational function. So this is an example of a rational function. So we have g of x equal to x squared minus 7x plus 12 all over x squared plus 9x plus 10 or 20. So I have a quadratic trinomial in the numerator. I have a quadratic trinomial in the denominator. What has to be true, or let's think about it this way, what number can you not have in the denominator of any fraction? 0. So think about what domain is. There's domain your x or your y values, your x values, right? So I need to figure out what are all of my possible x values that I could possibly have for this to be my domain. Well, I have x values in the denominator, which means I can't have 0 in my denominator. So I need to think about what values of x make my denominator equal to 0. Doesn't that look like a quadratic equation that we might be able to solve?
Oh, 5 and 4.
Factor it. Factors of 20 that get you to 9, like Ben said, would be x plus 5, x plus 4 equals to 0. So what values would get you 0, or what are your zeros? Right. So x would not be able to equal to -5 or -4. If it did, I would end up with 0 times -1, which is 0, or 1 times 0, which is 0, which means I would have 0 in the denominator, which means that can't happen. The world would explode if we tried to divide by 0 on our calculator. So my domain is going to be what? It's going to be all real numbers, except, right, so we're just going to write it out as our domain. It's everything with excluding, so x cannot equal -5 or -4. Let me make sure that we don't get really fancy.
Is this like what we did before with the exceptions?
Yes, with the exception stuff. Yeah, they don't get very fancy with their answers. I'm thinking advanced algebra in my brain right now. Yep, so we're good. Okay? That's it. So that would be your domain. So it's everything except the values of -5 and -4.
Just ignore the top of the fraction.
For now. For just domain. Okay? Got that? All right. So what are those values called? Excluded values. So those values in our domain that make the denominator equal to 0 are our excluded values. So here we have the definition that says real numbers for which a rational function is not defined. real numbers for which a rational function is not defined. Which leads us to something that's called an asymptote. We're going to learn about different types of asymptotes. The first one is the vertical asymptote. And remember, we kind of brought asymptotes into our lives when we were talking about exponential and logarithmic graphs. Remember I said make sure your graph doesn't cross the x-axis, because that's technically an asymptote, but never gets there. So that's what an asymptote is. It's an imaginary line that doesn't have a graph going over it. So to find a vertical asymptote, if x minus a is a factor of the denominator, which we know how to factor denominators, we just did that with the domain problem. So if x minus a is a factor of the denominator of a rational function, and here is a very important note, but not a factor of the numerator. So that means we're probably going to need a factor of the numerator. Then the equation x equals a is going to be a vertical asymptote. So if x minus a is a factor of the denominator of a rational function, but not a factor of its numerator, then x equals a is a vertical asymptote of the graph of the function. Okay? Verticals are the easiest ones to find. Pretty much you take those excluded values that we had from the domain. So in that last example that we just had, our two excluded values were what? -5 and -4. So the vertical asymptotes would be x equals -5, x equals -4.
And those would be vertical lines?
Right, so they'd be imaginary vertical lines that your graph would never intersect with. Random question? No, okay. All right, so. Am I doing something right now? There it is. It's not up here on my screen. Horizontal asymptotes get a little bit more confusing. This is a matter of memorization. So, if you have your rational function, where p is some polynomial in the numerator and q is some polynomial in the denominator, we have three things. So you're going to have 1, 2, 3 that you need to memorize. And this is just a matter of memorization.
Okay.
So you got to get this stuff stuck in our heads. So for number 1, number 1 is telling us if the degree of p, so that's the degree in your numerator, is less than the degree of q, so the degree in the denominator. So smaller degree on top, larger degree on the bottom. That's what this statement's saying right here. Then y equals 0 is your horizontal asymptote. So y equals 0 is always going to be your horizontal asymptote. So if you have smaller degree in the numerator than you do in the denominator, horizontal asymptote is y equals 0.
Is number 2 if it's the opposite?
That's number 3.
Okay.
Number 2 is if they're the same degree. Okay? So if the degree is less than the degree, or if the degree of p is less than the degree of q, then y equals 0 is the equation of the horizontal asymptote. Don't rewrite this again. That's going to pop up on the next screen. Just rewrite number 2. So smaller on top, y equals 0. Here my degree was 0 because it was a constant. Here my degree is 1. Smaller was on top. So I have a horizontal asymptote at y equals 0. Notice that this graph will never intersect my x-axis. It'll only get closer and closer and closer as it goes. All right, number 2 tells us when the degrees are the same. So if the degree of P equals the degree of Q, and we're going to let A and B are the leading coefficients of P and Q, then the equation y equals A over B is going to be your horizontal asymptote. So right now I got y equals 0. If the degrees are the same, so if I have a quadratic over a quadratic, like we did in that first example with the domain, then you take the leading coefficients of both of those quadratics and turn it into a ratio and then set it equal to y. And that's going to get you your horizontal asymptote. So if the degrees are the same, you take your leading coefficients, turn them into a ratio, that's your horizontal asymptote. Number 3 is if the degree is larger on top. Everybody ready for it? All right, so number 3, if the degree of P is greater than the degree of Q, then there are no horizontal asymptotes. There's none. So you've got 3 options. You got either 0 or none. If the degrees are the same, then it's the ratio of the leading coefficients. That's what we need to remember. So the hardest part is remembering which one's the 0 and which one's the none. So larger degree on the bottom, y equals 0. Larger degree on the top, there are no horizontal asymptotes. So those are easy to flip-flop around. If the degrees are the same, that's easy to see. Then you just take the leading coefficients. All right, so let's pick apart some rational functions and see if we can identify all the asymptotes. Ready? We good? All right, here's our first function. R of x is equal to x over x squared minus 2x minus 3. So identify vertical and horizontal asymptotes. How do we do the vertical? Set the denominator equal to 0. So x squared minus 2x minus 3 equals 0. What does that factor to?
X minus
3x plus 1 equals 0. Are any of those factors of your numerator? No. Our numerator is just x. If there was an x minus 3 up there, then I would ignore that, and that would not be a vertical asymptote. All right, so what do I get? X equals what? 3, and x equals negative 1. So there are your 2 vertical asymptotes. Horizontal. Not a lot of work. Just need to memorize it. Where's your higher degree? On the bottom. So it's either none or 0. Which one is it? It's 0. Y equals 0. Yeah, you got to remember that. Got to know the difference between them. Okay? Identified all our asymptotes. You're going to have to do that for the homework. Got it? We won't graph it yet. We'll save that for Friday. Next function. Y equals x plus 2 all over x minus 2. Here your vertical is really easy to see because it's already in factored form. What would your vertical be? X equals 2. Good. Now for your horizontal, do you have a larger degree anywhere?
No.
No. Degrees are the same. What's your leading coefficient of your numerator polynomial? What's the leading coefficient of your denominator? So turn that into a ratio. 1 over 1 is 1. So my horizontal is going to be y equals 1. Okay. If it would have been 2x plus 2, then my horizontal would have been y equals 2. If it would have been 2x plus 2 over 3x minus 2, then my horizontal would have been y equals 2/3. Got it? Okay. Let's do one that has, let's do one that has none really quickly. So let's do f of x is equal to x squared plus 1 over x minus 4.
Are we doing it as a class? Or?
Sure.
Okay.
What's the vertical?
X equals 4.
Vertical would be x equals 4. Horizontal would be none, because your higher degree is in the numerator. Okay? All right. So remember when we talked about vertical asymptotes, I highlighted that part that said as long as that factor is not a factor in the numerator. If that ever is the case, we get something, this is the last thing we have to do, something that's called a hole in the graph. This is it. We're almost done. We're going to do it.
Should we write all that?
Yeah. So a hole in a graph occurs if you have something like x minus b is a factor of the numerator and the denominator. Okay, so if you have a linear factor that is both in the numerator and the denominator, it ends up becoming a hole. It's not a vertical asymptote, it's going to be a hole in the graph.
Wait, I don't get the last part unless x equals
So
b.
then there's a hole in the graph of the function when x equals b, unless it's a vertical asymptote. Don't worry about that. Let's just worry about the first part. Don't even write the second part. Hole in the graph.
Wait, we're not writing that?
Don't write it. If you did, it's okay. All right, so let's look at something that would have a hole. Are you ready?
Wait, you crossed some of that off.
Yeah, let's just worry about that later.
Okay.
All right, here we go. Here's our function. Y equals 3 minus 2x minus x squared all over x squared plus x minus 2. Let's rewrite in standard form. So it'd be negative x squared minus 2x plus 3 all over x squared plus x minus 2. Now, since I see something really crazy going on, I'm going to start factoring things. First and foremost, what would be the horizontal asymptote? That's the easiest one to come up with. No. Look at your degrees. Be careful. Negative 1. They're the same. Leading coefficient of the top is negative 1. Leading coefficient of the bottom is 1. Negative 1 divided by 1 is negative 1. Right? Okay. So now let's go ahead and factor everything. So let's factor the denominator first. What does that factor to?
3 and 1.
No.
With a negative somewhere.
For the top, or the bottom one.
Oh, the bottom one.
Minus, yeah, x plus 2, x minus 1. For the numerator, let's factor out a negative 1 first. So if I take out a negative 1, then it would be x squared plus 2x minus 3. Oh, that's getting up there. So factors of negative 3 that get you to 2.
Negative 1.
So x plus 3, x minus 1 with this negative out in front. All right, so now I've factored everything. Do you have any linear factors in common?
No.
The x minus 1.
Yes, I have an x minus 1 in common. So that means I'm going to have a hole at that excluded value.
Uh-oh.
So I'll show you, well, when we get to the graphing, I'll show you what that means. Just right now, know it's going to be a hole. That second part of the statement that I crossed out would only occur if I had two sets of x minus 1s here. Like if this was x minus 1 and another x minus 1, then that x minus 1 would, what's the word I'm looking for? Take over, destroy that hole and make it become a vertical asymptote. Does that make sense? So if you had the same linear factor, then that would trump that and make it become a vertical.
When we're graphing it, what does the hole look like?
It's just a open dot. Just an
So
open
that's
dot.
like when we're graphing it, that's like.
All right, so my vertical. Excluding now that hole, what's the only vertical asymptote we're going to have?
1.
X equals -2, right? Because that's now a hole. Now let's figure out what the hole is going to be. So the hole, what's the excluded value here where it would be undefined?
1.
It would be 1, right? How do you think I get the y value of my hole?
Plug it back in.
Plug it back in, but I'm going to plug it back into what's left over when I take out the common factor. Right? So now I'll go down here. So I'm left with the function negative x plus 3 over x plus 2 when I eliminate the common linear factors. Right? So now if I evaluate that for 1, we get 1 plus 3, which is 4. So -4 over 3. So my hole is occurring at the point 1, -4/3. So that means if I were to go to graph that at that coordinate, I would put an open dot. Okay?
Look at that, we have 9 minutes.
Vertical, horizontal, hole.
Boom. What?
Do we need to do anything else?
Oh,